Dear colleagues, welcome aboard. This presentation is about a new solar heat exchanger, which is available for monetization. The idea, product development, as well as the drafting and submission of the patent were carried out by me, Andre Sueti, in 2024. This is my first personal patent to be monetized. This presentation is also my creation, and the narration was generated by a TDS system. My contact information is provided, but if you access this content through a broker or similar, please do not contact me directly. It is also possible that some brokers might remove my contact information, which is understandable. Please contact them for any matters. As a background, the invention is governed by the Coanda effect. For the purposes of this presentation, we are not concerned with any mathematical modeling of this phenomenon. It is sufficient to say that we are using its properties to our advantage. This GIF shows a common case of the Coanda effect in action, where water, initially in free fall, changes its course upon encountering the outer surface of the container, flowing around it and maintaining contact in a suspended manner. This was enough to inspire the idea. Imagine a simple plate whose upper surface is exposed to the sun, with the plate transferring heat to a liquid that flows from top to bottom via the Coanda effect on its lower surface. From there, we have a free source of energy for heating water, environmentally friendly. Moreover, we can already name our heat exchanger. Let's call it the Coanda Exchanger, in honor of the discoverer of the phenomenon. An extensive prior art search was conducted to determine if the idea is truly novel, and nothing was found. We are dealing with a genuine invention, real and incredibly efficient because the plate has a large area whose upper surface can be positioned perpendicular to solar radiation. The liquid is in full contact with the lower surface of the plate, with the heat collected by the plate being transferred to the liquid by conduction, which is the most efficient method of heat transfer. Plates are easy to cut, shape, and transport. Later on, we will learn about the heat exchangers available on the market, but for now, we would like to mention that they are based on tubes. When comparing the open liquid transport system of our Coanda exchanger with tube transport, ours has the following advantages. Without tubes, there is no pressure loss, which translates to low pumping power. Without tubes, there is no fluid restriction, meaning there is no clogging. Regarding a possible disadvantage of our system, at first glance, one might intuit that the open system of the Coanda allows for the loss of liquid volume through evaporation. However, fortunately, the fact that the liquid is transported suspended under an inclined roof means that the vapor, which naturally tends to rise, meets the liquid again. So the liquid carries the vapor with it, eliminating the possible loss. In fact, the vapor condenses when it encounters the liquid flow, as the latter is at a sufficiently lower temperature. In other words, the vapor is converted back into liquid, minimizing the loss to the maximum extent. At this point, we note that although the concept is clearly promising, it is still far from being a marketable item. I then developed the project to arrive at an efficient and economically viable product. Next, this product will be described in a very didactic manner, or as I often say, once it's ready, it's easy. In general terms, the product is primarily based on shapes formed directly in the plate responsible for heat exchange, which we will call the collector plate, with each shape serving a function to solve a practical problem. The first problem is to contain and distribute the liquid before the heat exchange. This is achieved by forming an open curve, called the inlet curve, at the top of the product. The liquid is pumped into the inlet curve, which naturally stores and distributes the liquid by gravity. We name the section of the plate responsible for heat exchange the collector curve, while the section that connects the inlet curve to the collector curve is called the accelerator curve. The accelerator curve must have a sufficiently large radius to allow the liquid to accelerate without dripping. If it is too sharp, dripping may occur. After the heat exchange, the liquid is collected by the so-called outlet curve, which, like the collector curve, stores the liquid and directs it to an external reservoir through a connection and a hose. Regarding possible vapor losses, it was mentioned that the vapor is carried by the liquid itself. However, the proposed layout allows a small portion of vapor to bypass the accelerator curve without coming into contact with the liquid. This vapor is collected through an additional shape called the condenser curve. Note that this shape directs the condensed droplets to the collector curve, eliminating waste. It is evident that, at this point, the concept is already technically functional. However, one can optionally increase the efficiency of the heat exchange by applying a greenhouse effect. The idea is the same as used in covered solar collectors, which will be discussed later. Simply install a transparent plate, called the insulating plate, over the collector plate and thermally enclose the assembly. The fact that the insulating plate is transparent allows solar radiation to enter and heat the collector plate, while containing the convection from the collector plate, a genuine greenhouse effect. The lateral sealing will be addressed later. Regarding an additional aspect, the use of flat and nearly horizontal plates allows the possibility of adding a second function to the product, serving also as an external roof. When applied this way, it may be desirable to contain rainwater. This problem is solved by optionally adding a third plate to the product, called the gutter plate. The gutter plate then collects the water that runs off the collector plate or the insulating plate when present. Having completed the functional overview of the product, let's now discuss its manufacturing. The fact that the functional components of the product are plates leads to using plates for the structural components as well. This reduces costs in machinery implementation, raw material inventory control, supplier development, and transportation of both raw materials and finished products. After significant concept development, a seemingly innovative technique was developed, which involves shaping the functional plates through their sliding in channels cut into other plates, called matrix plates. These matrix plates, after elastically shaping the functional plates, become part of the product, serving as structure and maintaining the shape throughout the product's lifespan. They also close the sides of the exchanger, providing hydraulic and thermal sealing, which is particularly useful when the insulating plate is present. For manufacturing the shaping profiles in the matrix plates, it is suggested that any well-known CNC cutting method, such as laser, plasma, or water jet, could be used. At this point, it is easy to deduce a highly functional assembly process. Simply use parallel spacers between the matrix plates to form a structure, and then slide the flat plates along their channels. The functional profile is automatically shaped. Moreover, if the plates are sufficiently thin and pliable, this process can be done on site. Both the functional plates and the matrix plates can be transported in their flat, stacked form and the structure assembled at the location. This saves on logistics, inventory, and transportation costs. In summary, the strengths of the process are few and common equipment required for manufacturing, few raw material items, efficient transportation and inventory. Therefore, the manufacturing implementation is relatively simple. Well, we've now covered the manufacturing topics. Let's talk about applications. As mentioned, one of the advantages of the plate-based concept is its applicability as external roofing. In this regard, the first application that comes to mind is positioning the product against an external wall, serving as both a water heater and a cover, as the image suggests. We would already have interested parties with just this product. However, the design includes another innovative feature. The inlet and outlet curves were designed to allow the exchanger to tilt without spilling the liquid. Imagine the exchanger is intended to cover a residential or commercial leisure area. It might be desirable for the cover to tilt at certain times to allow sunlight to enter, or to enable cleaning of the exchanger's external surface. Such tilting can be easily achieved by fixing it at a pivot point below the accelerator curve. It can be seen that the liquid contained in the inlet and outlet curves does not spill regardless of the position of the exchanger, preventing the ground and objects from getting wet. Another useful application is the modular one, which is also automatically resolved by the proposed design. Exchangers can be linked together, as well as mirrored, forming a double system. See the application of this version for heating a pool, where the exchanger is also used to cover a soccer field. A simple horizontal screen below the exchanger can protect it from being hit by soccer balls. Besides heating liquids, another extremely useful function of our Coanda exchanger is cooling environments. Imagine a closed and covered space, such as an event venue with a high number of people, under the strong summer sun. The sun heats the roof, which in turn heats the environment. Additionally, the thermal energy generated by the people also heats the space, and this energy is contained by the roof. Hence, the application for cooling environments arises. The simple and direct application of the invention as a cover for this space would significantly reduce the temperature inside. The water running under the collector plate cools the roof while also carrying away the warmer air from the environment, bringing comfort to the people. After the heat exchange, the water can be cooled by some known method, such as an evaporation chiller. Does any solar collector on the market do this? These were some comprehensive examples of the installation of the invention, which can be applied in much more specific cases, such as industrial ones, which we will not cover here. However, it is clear that the wide range of applications, combined with low manufacturing, operational, and maintenance costs, will create a commercially successful product. Moreover, it is worth noting that it is widely agreed that solar collectors for heating are more efficient than photovoltaic panels. We are making good use of free energy, aren't we? It's time to talk about business. The solar collector market is well defined and mainly consists of three types of products already mentioned: uncovered, covered, and evacuated. In general terms, uncovered collectors are the simplest, cheapest, and least efficient, mainly used for swimming pools. They consist basically of one or more black tubes exposed to the sun, through which the liquid is pumped and heated. By enclosing the tubes in a box with a transparent cover, we achieve thermal insulation combined with a greenhouse effect, creating a covered collector. Evacuated collectors, on the other hand, are more complex and expensive, as they consist of two glass tubes, one inside the other, with the air removed between them, providing more efficient thermal insulation and maintaining the greenhouse effect. The liquid inside the inner tube heats the working liquid circulating in contact with the tops of the tubes. Any of the three types of collectors can be applied wherever there is a need for water heating via solar energy, but as a general rule, uncovered collectors are primarily used for swimming pools, while covered collectors are installed in residences and commercial buildings, and are also used for swimming pools. Evacuated collectors, on the other hand, are more commonly seen in industrial applications. Due to the construction aspects of our Coanda, we expect it to capture a significant share of the uncovered collector market and a smaller share of the covered collector market. To be conservative, let's assume our invention will not take sales from evacuated collectors, although this is possible. Let's consider that, once established in the market, our product will capture 50% of the uncovered collector market and 30% of the covered collector market, which seems plausible. We say once established in the market because, as this is a new technology aiming to share the market with existing technologies, there is expected to be a market acceptance curve. This means that in the first year, the market share may not yet be as expected, while over time, sales will grow until they stabilize. However, to simplify the calculations, let's assume that the 50% plus 30% definition is an annual average that already accounts for growth. We also note that we are not considering the potential for a new market segment for the Coanda, as well as the novelty of using our invention directly as a roof. Additionally, we are not taking into account its applicability as an air cooler. We know there is also a market for air cooling through solar heating, which we haven't mentioned but does exist. In other words, we are being conservative in defining the 50% plus 30%, focusing only on the already established market. However, this serves as a starting point for conducting a quantitative assessment. We also need to discuss regionalization. There are determining factors for the application of each type of solar collector, such as the additional cost of covered collectors compared to uncovered ones may not make sense for heating a pool located in a hot and windless climate, as their efficiencies are similar under these conditions. On the other hand, uncovered collectors are less efficient in cold and windy climates, justifying the additional investment in a covered collector. Regarding evacuated collectors, in addition to the significantly higher cost, there are several countries in the world that do not have the technology to produce them profitably. This is one of the reasons why evacuated collectors are popular in countries with advanced manufacturing technology, such as China. However, as mentioned earlier, we will disregard evacuated collectors as our competitors. This market regionality is clearly illustrated by the graph shown. There is a complete discrepancy between the North American and Asian markets. Uncovered collectors represent 95% of new installations in North America, while they are negligible in Asia. The graph was obtained from SHW, or Solar Heat Worldwide. which is an annual PDF report from the Solar Heating and Cooling Program of the International Energy Agency, a global technology collaboration program. Their website provides useful data about the market. Through it, we quickly identified that the markets most interested in new solar water heating systems are China, India, Brazil, Turkey, and the United States, a valuable initial information for us. Continuing with the analysis and knowing that our product is well suited for pools, if we want to find out which countries have the largest installed markets for pool collectors, we have a ranking that follows this order: United States, Brazil, Australia, Mexico, and South Africa. It is noticeable that both the United States and Brazil appeared in both queries, indicating a potential target for initial commercial exploration. The SHW reports are a market data source. According to the website itself, Solar Heat Worldwide is published annually. Since 2005, countries, now 72, have provided data to create the most comprehensive assessment of solar heating and cooling markets worldwide. Our flagship report stands out for its detailed analysis of solar thermal technologies and serves as a reference source among international organizations, including the IEA, REN21, and IRENA. Using the SHW reports, we will extract information about the market from 2019 to 2022 in order to determine the commercial potential of our invention. This period was chosen considering that it includes the most recent available data, as the reports use data from the 2 years preceding the publication, so there are no data for 2023 and beyond. It was also carefully checked against the pre-pandemic period, and the conclusion is that there were no abnormalities in the statistics. The pandemic did not affect the solar collector market. Speaking about uncovered collectors, we've already mentioned that the market is concentrated in the United States and Brazil, where the technology is being increasingly used, while the rest of the world's market share is negligible. This graph summarizes the growth. It is found that the Brazilian market for uncovered collectors grows at an average rate of 860,000 square meters per year, compared to 119,000 in the United States, totaling 979,000 square meters per year. As we expect to capture 50% of this market, this means selling 490,000 square meters per year of Coanda collectors in the Americas. Regarding covered collectors, while the United States does not have a significant market for new installations and Brazil is only moderately relevant, the rest of the world is increasingly using them, with China being the country of greatest interest, followed by Turkey. Looking only at the Brazilian market, we can estimate an average growth of 715,000 square meters per year for covered collectors. 30% of this amounts to 215,000 square meters, adding this to the previous 490,000 square meters. We exceed 700,000 square meters of Coanda collectors sold annually in the Americas. A reference on costs is now needed. Average cost values per area were not found on official websites, such as the U.S. Department of Energy or the International Energy Agency. What is available online are independent articles, often produced by the collector's own manufacturers from various parts of the world. For our estimates, we will use an article from the Whole Building Design Guide website. This choice is based on it being a U.S. reference, apparently neutral, and updated by the Federal Energy Management Program of the U.S. Department of Energy. The information obtained indicates a cost of $10 to $40 per square foot for uncovered collectors and $90 to $120 per square foot for covered collectors. Averaging these costs and converting to square meters, we arrive at a cost of $270 per square meter for uncovered collectors and $1,130 per square meter for covered collectors. We estimate that our Coanda will be cheaper than uncovered collectors. If we assume it costs 70% of the covered collectors, that equates to $190 per square meter, which still seems high for a product primarily made of cut sheets and with a lower power pumping system. In my opinion, there is no reason for a Coanda to cost more than $120 per square meter installed, but this requires more detailed analysis. For now, we will be conservative and consider the $190 per square meter, expecting a high profit. At $190 multiplied by the forecasted 700,000 square meters, this generates $13 million per year, which can be exclusively explored until 2044. Deducting the first year for product development, this amounts to $247 million over the remaining 19 years, considering only the Brazilian and US markets. Now, if the business plan also includes China, the business potential skyrockets. China has an average growth of a staggering 6.4 million square meters of covered collectors per year. 30% of this is 1.9 million square meters, resulting in an additional $364.8 million per year. When added to the $13 million from the America, this totals $377 million per year, or more than $7 billion over the patent's lifetime. In summary, we are looking at $1 billion potential. To achieve this, the first concrete step has already been taken, which was the patent filing. It is now time to discuss the patent. The patent includes 1 independent claim and 9 dependent claims. The independent claim protects the application of the Coanda effect in sheet-based heat exchangers. In other words, it protects heat collectors that comprise at least one collector sheet, with its upper face exposed to the sun, while the liquid to be heated flows down the underside of the sheet. As mentioned earlier, an extensive prior art search was conducted through a SpaceNet, Google Patents, PatentScope, USPTO, and INPI databases, and fortunately, nothing compromising the patentability was found. The other 9 claims, which are dependent, provide detailed protection for the main invention. They cover the non-linear profile along the transverse axis of the collector sheet, the inlet curve, the outlet curve, the insulating sheet responsible for the greenhouse effect, the modularity, the equipment for heating that utilizes the heat exchanger, the equipment for cooling environments that utilizes the heat exchanger, the use as roofing, the mobility of the cover. The description followed the best patent drafting practices of WIPO, being written in a clear and concise manner, leaving no doubts about the claims. The drawings were also prepared according to the recommendations. The patent was drafted in English and filed internationally on June 2, 2024, under the rules of the Patent Cooperation Treaty, with all filing fees paid and no pending issues. The other relevant dates are, by October 2, 2025, the international search opinion will be available from the RO office, usually occurring earlier. Based on the history of the chosen RO, in this case, the Brazilian office, it is expected that the opinion will be available around February 2025. After the issuance of the opinion, an early publication of the patent can be requested at no cost. If no action is taken, the patent will be published on December 4, 2025. If one wishes to publish it before the search opinion is available, a fee of 200 Swiss francs must be paid to the International Bureau. If one does not wish to publish the patent and prefers to keep it confidential, a request must be made by November 19, 2025. From February 2, 2026 to December 2, 2026, it is necessary to select the countries where the patent will be filed, entering the national phase. After that, deadlines are dictated by each office, with the priority date being the same for any country, June 2, 2024, which is the date from which the patent is actually protected. In addition to the English drafting, which is accepted by most offices, the patent is also written in Portuguese, which may facilitate the patenting process in Brazil. Yes, Brazil speaks Portuguese. Speaking of the Brazilian filing, there is also a program from the Brazilian office, INPI, called Patents Verdes, that accelerates the granting of patents related to environmental preservation, including renewable energies, as is the case with our invention. With this program, it is expected that the patent will be granted in around 2 years, based on information from INPI itself. Well, we have reached the end of the presentation. To recap, I had an idea, which evolved into a product, leading to the drafting of a patent that was filed internationally. The market was analyzed, and now it's time to monetize this patent, passing the baton to someone with the potential to bring the product to market. The next step is yours. I look forward to your contact. Thank you very much.